Welcome back, and we are going to continue talking about inverse functions. We want to actually be able to start to find the inverse function rather than just talk about things around it. So the first thing that we have to satisfy when we have inverse functions are called cancellation laws. Okay. The book just calls it the definition of inverse functions, so I like to call them cancellation laws. You have to satisfy both for an inverse function. Okay. So here we go. Just kind of walking through the definition. So we have to have a one-to-one function, injective, right? And then we have f with a superscript of -1. Now, I have to stress this. You'll see it here and then down here too. This is not, so normally it's not an exponent. We normally have superscripts mean exponents. When we're talking about functions, superscripts are not exponents. Okay, generally speaking, okay, particularly the -1 superscript does not mean 1 over. Okay, so do not do this. Do not do this. Okay, I see it happen all the time. That's why I'm stressing it. Okay, anyway, for the inverse function, okay, we have to satisfy these two cancellation laws. F of f inverse of x is equal to x, and f inverse of f. Okay, so this, again, if you remember what composition means, this just means that you would have f, and then into the f function you have to insert f inverse, and then when you do that composition you get x, and the other way would be f inverse, and then into the inverse function you stick the original function and it outputs x. Okay, you do need to do both. Okay, so both of these have to be satisfied. Okay, and so this is just going to allow us to verify if functions are inverses or not. So we have 3 examples. I'm going to do the first 2, you're going to do the last one. Okay, are these functions inverses? Okay, I'm labeling them as f and g because I don't know. So let's check. I need to do the composition. Okay, I'm going to do f of g of x. Okay, so again what this means is into f I insert the g function. Okay, and when I do this, okay, so then let's see, the only place where there's an x is right there, so I'm going to replace that x with 2x minus 6, and then what was that, plus 6? Yep, plus 6, and then over 2, so then simplifying I get 2x minus 12 plus 6 over 2. Let's see, those combine and I can reduce. Okay, I'm doing a little bit of work in my head, but I end up getting x plus 3, or x minus 3 rather. Okay, which is not equal to x. Okay, so since it is, I'm comparing it to x because that's what, if I do the composition, I should get if they're inverse functions. So consequently, since it is not equal to x, I'm going to say not inverse functions. Okay, doing the same for f and g for the second set here. Okay, now, okay, let's do the composition. Okay, so I do f, and then into f I stick 2x plus 5 over x. Okay, and then that's going to all go into this little x here. So then this is going to be 5 over, and then 2x plus 5 over x minus 2. And then you look at it and you cry a little bit. Okay, well, crying isn't going to help. We need to get over ourselves and move on. So find a common denominator. 5 over, and then 2x plus 5. And then the common denominator is going to be x, so I can write it like that. And so I have minus 2x all over x. Okay, the 2x's are going to reduce, and so really at the end of the day what I have is 5, and then this big bar means divided by, right? Divided by 5 over x, so then I have 5 times the reciprocal, x over 5, and 5's end up reducing, and I get x. That's good. That's good. Okay, but it's not the whole story, right? I need to do the other composition, or the composition in the other order. Okay, so this is good, but I also do need to do into g, I need to insert the f function. Okay, 5 over x minus 2. Okay, and so I'm going to insert that for both occurrences of x. So I have 2, and then 5 over x minus 2, okay, plus 5, all over, and then it'll be 5 over x minus 2. Now this one, again, looks scary. Cry a little bit, move on, get a common denominator. So this will be x minus 2 over x minus 2. Okay, and let's see, so then I end up with 2 times 5 is 10, x minus 2, plus, and then distributing the 5 to both of those, so I'd get 10x minus, oh, nope, JK, back up, 5x minus 10, all over x minus 2, and then 5 over x minus 2. Now, at this point, I'm going to do a little simplification that you're going to think is a trick. It's really not. Notice how all the denominators are x minus 2. What I could do is multiply all the denominators, or all the terms in here by x minus 2, which would effectively clear the denominators. Okay, so I can just drop them. Okay, once you get all the same denominators, drop them. Okay, and so consequently I'm left with the numerator being 10 plus 5x minus 10 all over 5. And certainly the 10 and minus 10 reduce, and then the 5 and the 5s will reduce as well, and I end up with x. So that's also good, right? I did the composition in both orders, got x. So I'm satisfying both of the cancellation laws. Okay? So, consequently, since both of them are satisfied, I'm going to say yes, f of x and g of x are inverses. And I can even say g of x is equal to f inverse, so superscript minus 1 of x. Okay? Now for h of t and k of t, these are a little interesting to work with. I want you to verify if these are inverse functions. So again, you'll have to do the two compositions. Okay, so do it and then resume the video when you're ready to see the solution. Here's my solution. So I did the composition in both orders. I got t, we're going to t instead of x. Big deal. Okay, and so when I did the composition in h of k, right, stuck k into h, got this. Now technically, right, when you take the square root of a square, you should get absolute value. But the thing is, because of the domain that we're on, so k, when we were working with k already guaranteed that t was greater than 0, so we can really just get rid of the absolute values. Okay, square root of a square, absolute value. Okay, when we square a square root, though, it doesn't matter. Okay, and so here in the other order, we end up getting t, so then they are inverse functions. Okay, so big, or the punchline here, to satisfy inverse functions, or for inverse functions, if they are inverses, they need to satisfy the cancellation laws.